So whilst we're speaking about triangles, let's look at congruent triangles. Yeah. And you will remember, or you may remember, that if you're going to prove something is congruent, basically you need 3 pieces of information. All the different tests have 3 pieces of information. So every one of those proofs, though, require a side or a corresponding side in both to be equal. Because if we don't have a side, then the best we could do is prove they were similar, not congruent. So we need to know at least one side. So if you're looking for it and you're struggling, I guess that's the first thing to look for, because we know we've got to find at least one side that's going to be the same. And so the different tests, it could be in fact that, hey, look, all the 3 sides of this shape are the same as the 3 sides in the other shape. So, oh, look, that one's the same, and oh, so is that one. Oh, what do you know, the third one is as well. And so that would be a case of what we call side, 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 which we abbreviate SSS. So then the second one then is, well, we'll take away one side and we'll add in an angle. But you may recall that the actual angle, it does matter which angle. It has to be the one that's in between the 2 sides that you've shown are equal. So that's why we say side, angle, side, to highlight the angle must be the one that's in between, what we call the included angle. So side, angle, side. So there's our second one. So all right, take off a side, add in another angle. So Angle-Angle-Side. So this time we know 2 of the angles are the same. And I guess by angle sum of a triangle, that means the third one's going to be equal as well. But as I was saying, that only proves it's similar. So we need to know one side. But that side has to be in the same position or corresponding in both. Can't just be any side. So the one I've marked in here is the one that goes from the angle I've marked with a dot and the one I haven't marked. So it must be the same position in both triangles. Now the fourth one is just a specific case, that being right angle hypotenuse side. So if we know we've got right angle triangles, we know that the plural of a hypotenuse and one of the other sides. So say it's actually a special case of the other ones. You could bring it back to any of the 3. Because I know 2 sides are equal, I could use trig to then show that another angle is equal, and I've got angle-angle-side then. Or I could use Pythagoras' theorem and find the third side, and I'd have side, side, side. So I could do any of the 3, but we just summarise it because it's a special case, right angle triangle. We've got right angle hypotenuse and side. Let's do what is now a very old question, 1985. Goodness me. So this is the shape they gave us in the question. It is, of course, a quadrilateral. And we've drawn in 2 diagonals. They've told us they intersect at right angles, and DAS is the same as BAS. And they just want us to prove that DA is equal to AB. All right. Well, I did that via angle DAS and BAS. Well, they've told me they're the same. So that information was given to me. Sometimes we like to just write down, okay, I found an angle. Because I'm looking for 3 pieces of information. So, righto, I've got one bit. The side AS is common in both of these smaller triangles I'm looking at. So I've got a side that's the same. And DSA is the same as BSA is 90 degrees. They told me that. Now, by the way, if in a diagram they've just labelled one's a right angle, you don't have to say, oh, well, ASD is 180 minus the right angle, therefore it's a right angle. If they've told you these lines are perpendicular, it is okay to say any of them are 90 degrees. You don't need to waste time. And so I've got angle-angle-side. So what was I saying? Oh, yes. So DA is in fact equal to AB. Matching sides in congruent triangles. Now we're going to prove DC is equal to CB. So in the larger triangles I'm using this time, DA and AB, well, I've just proven they're equal. Angle DAS and BAS, they were given to me. And AC is common in the larger triangle. So that one was side angle side. And once again, then it's just matching sides in congruent triangles. I get that those 2 sides we're looking for are indeed equal. All right, so whilst we're talking about triangles, remember we have some special triangles There's the isosceles triangle where two sides are equal. So if I know it's isosceles, I can say, oh, well, therefore AB is equal to AC, because they are equal sides in an isosceles triangle. Or if it's the angles I want to use, that fact, well, okay, angle B is equal to angle C. Now, there's different things you can write. I've written equal angles in an isosceles triangle. Some people write base angles in isosceles triangle are equal. That's fair enough. But remember what I was saying yesterday. Don't assume it's isosceles. If all they've told you is AB is equal to AC, technically, you don't know it's isosceles yet. You've got to prove it as part of your proof. The way around that, of course, is in your reasoning. Instead of saying, say it is that AB is equal to AC that they've given you, and you want to just simply say, well, angle B is equal to angle C. Instead of writing equal angles in an isosceles triangle, you can say the sides opposite the equal angles in a triangle are equal. And so it's a way around, I guess, of not having to prove it's isosceles. But that will always be true, of course, via the sign rule. Because remember, sine A on A will equal sine B on B. So the side opposite equal angles must always be equal. The equilateral triangle is when all the angles are the same, all the sides are the same. So my reasoning there, geometry is strange. When we're doing algebra, normally we don't put more than one equal sign on a line. Geometry is the exception here because we're listing all the different things that are equal. So AB is equal to AC is equal to BC. They are the sides in equilateral triangle. I don't need to say the equal sides because they're all equal. And angle A is equal to angle B is equal to angle C is equal to 60 degrees because they are the angles in an equilateral triangle. Some terminology with triangles. That's a triangle. That's the first bit of terminology. All right, altitude. Remember, altitude is just another name for perpendicular height. Okay? So it goes from a vertex and is perpendicular to the opposite side. So the perpendicular height. Then we have what's called a median. Now, median, you might remember that word from stats, where it was the middle of the information. Same deal, it means exactly the same thing. Median is middle. So this time we join the vertex, instead of making it perpendicular, we join it up to the midpoint of the opposite side. So that's a median. And then we have the right bisector. So it's sort of like the combination of these two ideas. It's just that they won't necessarily go through the vertex. It's the line that's perpendicular and goes through the midpoint of the side. So clearly in this triangle, it's not going to go through the vertex. In an isosceles triangle, and if I was to drop that perpendicular height down, it would in fact be the same as the median and the right bisector. And in fact, in an equilateral triangle, they would all be the same. Okay, 8C.